What's up, everybody? Welcome back to another Kill Teaches thing. I don't know what I'm gonna call these. They're weird. So, dog, get out from under my legs, please. I love you, Charlotte, but stop. So today what we're gonna be doing and what we're gonna be going over is we're gonna be doing simple harmonic motion. We are gonna be doing talking about springs, and we're doing some practice with that. Just as a little bit of a reminder from when my students were last in class, we were doing springs last. And we were going to be doing a practice day, and of course, then we got the call that we're not in school anymore. So let's jump right on in, doing some of this stuff. So we have a body of mass, which is 5 kilograms, and it's suspended on a spring that stretches down 0.1 meters, where the mass was attached. The body is then displaced downward an additional 0.5 meters and is released. What we are tasked to do in part A is to calculate the period, frequency, and amplitude of the motion. So let's get right on into it. So first things first, this will be math. Yes, I said multiple times, AP Physics is a very math heavy course. So first things first, our amplitude, which we signify with an A. Our amplitude is just the amount that we have moved it from its 0 position. And so that basically is just going to be for us that 0.05 meters. So that's what's going to be our amplitude. Super duper easy peasy. Now, finding the period and the frequency, those are the things that are harder. So we remember period is signified with a T, and our equation for finding period of a spring is actually 2 pi times the square root of m over k. And so that's what our equation was. That's what we had found back in our previous section before all of this started, and we had to start doing online. And so that's what we have. All right, so that's super duper easy. Well, there's a couple of things that we don't know yet. Like, we don't know what K is. We don't know what the stiffness of the spring is. So I'm going to slide on over here, and we're actually going to do some stuff with it. So we had our mass as it's attached to whatever thing that it's hanging from. And it has, of course, our spring, our very greatly drawn, I'm such a beautiful artist spring. And our box, or our mass, that is equal to 5 kilograms. Now, thing is, we have a couple of forces. And so what we're going to do is a free body diagram. Now, a free body diagram just shows us the forces that are acting on an object. So going down, we have the force of gravity. It always pulls things down. We designate that with m times g because it's just the mass times the gravitational pull of the earth. And then up, we have a force that's not letting this thing fall to the ground, and that's our spring force. And so our spring force is also negative k times x. Now, this thing is at equilibrium. Equilibrium means that the sum of all forces is equal to 0. I know I'm doing terrible because I have to write on the computer screen, but so it means that the sum of all of our forces is equal to 0. That means that my spring force, when I subtract my gravitational, is going to be equal to 0. So what I got to do, boom, I just add my mg to the other side, and we now know that our spring force is equal to our gravitational force. The only thing left we have to do is we have to solve it for k, right? Well, for solving for k, we just divide by an x on both sides. It cancels on this side, and we're left with negative k equals mg over x. And that's what we're left with. So that's how we're going to find k. And that's pretty much how you're going to find k most of the times with a vertical spring. And it's really, actually, that's pretty much it. That's what we do. So now we just plug and chug. We know that our mass is equal to 5. Because that's what the problem told us. Gravity is a constant, so what it's equal to is 9.8, which is super awesome. So does our spring force always equal mg? Our spring force, in this case, it does. So the reason why it does in this case is because of our free body diagram right here, this guy. We only have 2 forces acting on it. And so because we only have 2 forces, our mg and our negative kx, when we go and we look at the sum of all of our forces, which is our forces going up minus our force going down, it's equal to 0. If we had any additional forces in it, we would have to add them in right there at that point in time. Now, luckily for us, it really is just these. And most of the time on the AP things, they're not going to add in more. So since we're not going to add in more, that'll be pretty much what it is. Now, last we have to divide by our x, which is how far it's moved. Now, the thing is, you might be like, well, it moved 0.05 because that's what our amplitude was. And, you know, I'd be very much to be like, yeah, that's a really good idea, but it's not. That's how much we additionally moved it. We're looking at this thing when it's at equilibrium, when it's not moving. So if we look back to the problem, we can remember that this thing, when we put the mass on the spring, it moved 0.1 meters. So it just moved 0.1 meters. And so that right there, that's what our x is. That's how far the thing has moved from equilibrium. Meaning that we have this all divided by 0.1. Now, 5 times 9.8 is 49. I know that off the top of my head because it's half of 98. And then we have to divide that by 0.1. When you divide that by 0.1, it's going to move the decimal over, giving us 490 newtons per meter. And it's going to be negative because it's negative K. We just have to move our negative over. But not that it really matters, because technically this distance is also a negative distance because it went down. So it's taken care of. We really don't have to worry about that. So we know that our K is equal to 490. That means that I can come back here and I can plug everything in to my period equation. So we have our 2 pi times the square root of 5 over 490. Now, the way I generally like to do this, I like to do this in steps. So I guess I should find my cellular device so I can do that. I don't know where my cell phone is. There it is. So the big thing I'm going to look at first, right, as we're doing these things, go and pull out my handy dandy calculator. So we do 5 divided by 490, which gives us 2 pi times the square root of 0.01. Awesome possum. Now I have to turn my calculator sideways. All right, so I go and I take the square root of that guy, and that gives me 2 pi times 0.101. Sweet. Now I have to multiply this by 2 and multiply it by pi. Where's the pi button on the iPhone? There we go. And so when you multiply it by 2 pi, that gives us a period of 0.635. And that's going to be in seconds. And that right there is our answer. And that looks like that should be an S. It's an S. We're going to call it an S. So 0.635 seconds is our total period to do this. Now, that gives us the period, but we're still missing the frequency. God, I wish I had used my whiteboard. I could use my whiteboard. I don't know that it'd be easier or not. So the next thing that we have to do, and I'm going to go out further to my side because I don't have room on my paper to do this, and I'm so sorry about that, is when we try to find the frequency, we know that it's just equal to 1 over the period. So 1 over the period, 1 over 0.635. When you do 1 divided by 0.635, you end up getting a frequency of 1.574. And that's in hertz. And I know this math is probably hertzing you. And so I'll add in the pun to make it worse. And that was the first question. I did. It's true. Though the class had a population of 4 when I was teaching it too, so. Now, next we're asked, does the amplitude have anything to do with the period and frequency? Well, if we take a look, our period equation doesn't have anything in there with amplitude, and our frequency equation didn't either. So, no, it doesn't. It does nothing. It has nothing to do with that. So, easy enough. Now, the next question is, what's the equilibrium position for this mass? Now, the equilibrium position for this mass ends up being 0.1 meters. And that's just because, that's the position that it stretches at rest. Oh, that's what you meant? Nice. All right. Now, the next thing is we got to find the maximum speed of this mass, and we want to know where it occurs. So that means that we're going to be looking for our Vmax, and I'm not going to go through the math for all of these. That's going to take too much time. So if you guys want to calculate it on your own to make sure that I'm right or wrong, then that's fine. Now, to find that, we do K over M times A squared, and that's how we find the maximum velocity. So when we plug everything in, we take the square root of 490 over 5 times our amplitude, which our amplitude, as we said, was 0.5 or 0.05. We got to square that. When we plug all that into our happy, beautiful, glorious calculator, and we do it correctly, what we should get is 0.495 meters per second. And the point that this happens is as it passes through the happy equilibrium point. And so that's what we end up getting. Yeah, that's my roommate. It's like, I like how I just see somebody's legs back there. But yeah. My roommate. All right. So, next one for us. What's the maximum acceleration and when does this happen? All right, so now we have to go into our maximum acceleration equation. And so Amax, we can find that by using negative K over M times A, times our amplitude. And so what that's going to be is negative 490 over 5 times 0.05. That's it. Super easy. We plug it in, and what we end up getting is actually negative 4.9 meters per second squared. Now, the thing is, when does this happen, right? That's our next point. Well, this happens at the positive and the negative amplitude. And that's it. At positive and negative amplitude positions. That's when we generally find our maximum acceleration. There is a lot of blue on my screen. So, that's what it is. Yeah, I know it's a lot. It is an AP class, so there is that much going on. Not to mention it's AP physics. All right, so part F. We're asked to find what the energy of the system is at the lowest point and when the mass is at equilibrium. So we have to do this in two different ways. So when we're at the lowest point, what we have there is we have no potential energy from gravity. And we have no potential energy from gravity because it's at its lowest point. And our potential energy formula for gravity is mass times gravity times height. And so if we have zero height, we have no potential energy from gravity. Now, we have no kinetic because our velocity at an amplitude is 0. Velocity is equal to 0 at an amplitude. So that's the way it goes. Which means that for this, there is only potential energy of a spring. And that's it. That's all we have is spring potential energy to solve this out. And so that means that we have to use our potential energy of a spring equation, which is 1/2 kx squared. Would it scare you guys to know that I have all these memorized too? Spooks me. So we take that. We have our 1/2. Our k is 490. We're at our lowest point. I shouldn't scratch that out. We're at our lowest point, so let's highlight it. And what that means is that we're at our amplitude. And so we will have to use our 0.15 there because that's how far away it is. That's how the total stretched it is away. Because we got our 0.05, which is our amplitude. That's our added amplitude. And it was 0.1 already down. So we have to add those together to make it actually work out. Now, when you plug this all into a beautiful, glorious looking calculator, generally I prefer a TI-84. I prefer my color edition, but I think it's dead. You end up getting 5.51 joules. Awesome. Happy day. That's spectacular. All right. Now, I am going to be using this next part to prove something for you. If you've been in the class and you've taken physics and you understand already, you should know, and it should make sense, well, that this energy would be the same, right? That the energy at the lowest point should be equal to at the equilibrium point. The thing is, I want to prove that that's correct. So we're going to do it. So, at our equilibrium, we know that our V is going to equal V max because that's the fastest it can go. We know that our spring length is equal to 0.1. And we also know that our height for our gravitational potential energy, I should put that as PE sub G. Our height for that is 0.05 because that's how high up it is from 0. So, if you're confused by that, I'm sorry. I would draw it out, but I'm not going to. Mostly because generally I think that if you're not quite sure what all is going on, it's probably because you're not taking an AP physics class, which is fine. And you really just need to it's okay. So now we get to do the fun part. So we got to find out what our energy is equal to. So energy is going to be equal to mgh, right? We have that plus 1/2 mv squared. And then we also have our spring, which is 1/2 kx squared. So we have to then plug in all the numbers for this and plug it into our calculator and hope that we get the same answer that we did last time, or at least close enough to it that it makes it be like, oh, okay, then it's rounding error. Otherwise, something went wrong in the universe. Spoiler, it didn't. So now we just plug everything in. So we have our 5 times gravity, which is 9.8, times 0.05. And that's our gravitational potential. We have 1/2 times 5, which is our mass, times our velocity, which is V max, which we said was 0.495 meters per second. And we got to square that number. Then we put in our 1/2 times K, which is 490, times X squared, which is 0.1 squared. It's not even a full energy equation. It's glorious. On the bright side, nothing's rotating, so we don't have to add in a rotational kinetic energy. So Now we plug this all into our calculator, and you know what? You guessed it. You are so smart and so wonderful that you already knew that it was going to equal 5.51 joules. And you're glad that your physics teacher taught you how to check your work, so that way you made sure you were completely right. There we go. Sweetness. I made a bad box because it's covering up the next question. And now we move on. So, next it wants us to graph this difference in energy. So, the energy that we're doing, and we're going to be looking at a different energy equation. Now, we understand that there's this 5.51, which is our total energy throughout the entire system, right? So that's our energy tot. It's our tater tot because we eat all of them. It's our total. You always eat all your tater tots. So, then what we have to look at is we have to look at both our kinetic energy, our spring energy, and our gravitational energy. So what we have is you know what? I'll even use different colors for you guys. So orange, this is our spring energy. As we move from Y min to Y max, what we end up happening is we actually have it going down. And so that's our potential energy of a spring. It ends up going down while that goes. Now, our potential energy for gravity, or gravitational potential energy, it ends up going up over time because we get higher. We get higher to a point where it's going to be fully there. So this is when we have our potential energy of gravity. And it goes up all the way. And so then our last one that we have is our kinetic energy. And our kinetic energy is very interesting because it goes all the way up till it gets to its equilibrium point, and then it goes all the way back down. And so that one right there, that's our kinetic energy. And it does that because whenever it's at a max or a min with a spring, it has no velocity. If you have no velocity, you have no movement. No movement, no energy. No kinetic energy. So that's what goes on with that one. And that right there, boys and girls, is how you science that. I guess it's not real. I mean, some people would argue that this is just math, but math is just a way to express the science and the knowledge that we already know. So you can fight me on it. Now, there we go. That's question number 1. How would it feel for me to tell you guys that we only have 2 questions today and the first one took us 22 minutes? So, just to understand, by the way, just so you guys understand and everything that's going on, AP Physics is also considered the hardest AP class to take and has probably the hardest AP test, which is why we're also incredibly thorough, and we want to make sure that we can give any student that sees this the best chance they can going forward. Yes. Everything. My class. No, somebody already said in chat that I'm flexing right now, and I can't really say that I'm not because this is what my degree's in. There we go. All right. So let's do up this next question. All right. So now we have a spring. It's on a horizontal surface. Oh, springs on horizontal surfaces. I don't think you guys understand. They're so much easier. They're so nice. It's just like, wee, here's a spring and there's a thing. Woohoo. So that's it. That's super easy. Nice and positive. Oh no. Engagement's great. I like reading what you guys are saying. And if there's a question that is actually viable to what I'm talking about, I will stop to read chat and tell you guys. Z's already asked a couple of really awesome questions that I wanted to make sure got into the video. So, because I didn't start this at 0, right? I didn't start with projectile motion and go through the entire thing and teach everything. So there's stuff that you guys might not know, but you want to learn it. I want to be able to answer questions. So if I think the question is actually, it's different from my actual classes, right? I can't just ignore questions in actual class. I can ignore your guys' questions if I don't think that they're on track. But if it's on track, then I can add it in and definitely think that it's helpful, because if one of you guys doesn't understand what's going on, then somebody that's watching the video won't understand what's going on. And so if only 5 people understand what's going on, it's different, you know? They should be. They've been told to. I'm posting it to YouTube as well. But I do have some kids who are supposed to be watching. And I know that some are watching, so. Yeah. And see, that's the thing, like, Divinitus is one of my students. He's going to have to rewatch. And then Blake's another student who's going to have to probably rewatch. So I'm going to be putting it up there anyway. So, so we have a horizontal spring. It has a spring constant of 200 newtons per meter. It's mounted horizontally on a frictionless surface or near frictionless surface. So we don't have to worry about the force of friction. Thank God. Now, one end of the spring is attached to a fixed wall and the other is attached to a mass of 2 kilograms. The block is pulled inside a distance of 0.04 meters and then released. I will have something for my regulars and my AP to do on Google Classroom to show that they have gotten the understanding from the notes. So you guys won't have to turn in notes, but you guys will have things there to show. And if you don't have internet access, I would probably ask you to just send me a picture and I'll send questions and stuff like that home. So hopefully email will still work even if you can't get to Google Classroom. So we got it figured out. I will, in the first 2 weeks, we're not even supposed to be like grading anything. So I'm just making sure that you guys are getting stuff in because it's different. So yeah. All right. So frequency and period of this wonderful thing. This equation, will it look different? It actually won't look different at all. So since it's going sideways, it makes it easier for us, right? So really what we have here, if we're looking at a force diagram of this thing, all we have is we have our spring force acting back, and that's it. So we don't have any other force to go with. So our equilibrium, our forces, the only thing that's acting on it is the spring force. So there's nothing else we really have to find, but we're also given K, so we don't have to search for it. So that's the big difference with this, is that we were given our K, which is the toughness of a spring. That's what the spring constant is. This guy, he's the toughness. And so we already have that, and we just get to add it to everything else that's going on. So for our period equation, we can still use that same T equals 2 pi times the square root of M over K. We still get to use that guy. That's the same equation we get to use. And it's wonderful. We love this equation. It's awesome. By the way, most of the time equations stay exactly the same. It's like adding extra little parts to it. It's like all this stuff. So this formula, this is for period. So that's what we're doing here. This one is for the period. That's what we're doing. Period frequency. Yeah, what's up? How you doing, juicy doodles? So this is the period. So that equals 2 pi times the square root of the mass over the spring constant. So that's 2 pi times the square root of 2 over 200. And that's what it is. And so then when we plug that in, you do your 2 divided by 200 and you get 1/100th, and then you take the square root of that, which would give you 1/10. And so then you have 1/10 times 2 pi, and 2 times pi is 3.14 usually. So you'd have 2 times 3.14, which is 6.28. So then you have 0.1 times 6.28, which gives you a period of 0.628 seconds. If you don't trust me, you can plug it into the calculator. Then what we got to do is we also have to find the frequency. Frequency is equal to 1 over T. We take 1 over 0.628. I can't do that one in my head. So when you end up plugging that one in, you end up getting 1.592 hertz. Which I will say, the other thing is I do actually have I do have an answer key with me to double check my answers, just so you guys are aware. So I am prepared. So now we're asked to find the maximum velocity. Again, this is really easy. We just do the same thing we did on the other side. So we just do our Vmax, and that's equal to square root of K over M times A squared. And so what we do is we just plug and chug. That's it. Plug and chug. So we take the square root. We have our 200 divided by 5. Nope, it's divided by 2. I lied. It's divided by 2. 5 was the last one. Remember that after I wrote it, of course. And then we have to multiply that by our amplitude. Well, if we're looking in here, our amplitude, as we're going to pull it out, actually ends up being that 0.04. So that 0.04 is our amplitude. And so that's what we get as we go forward. So that's 0.04. We got to square that. So then we have to take, and we have to do the square root of 200 divided by 2 is 100. 0.04 squared is 0.0016. Multiply that by 100 would be 0.16. Square root of 0.16 would be 0.04, which, boom, double check. Oh, I was off. It's actually 0.4. Darn. I was off by a little bit. Actually, no, that does make sense. I was dumb. So it's 0.4. I always hate doing decimals. Well, 0.4 is what we get for our mass pounds. Oh, well, my mass, well, for our velocity, and that's in meters per second, as I lose what I'm saying because I'm trying to be silly. So then we have to find our Amax, which is our maximum acceleration. And Amax is equal to negative K over M times our amplitude, which is awesome and spectacular and everything that we know and love. We have negative 200 over 2 times our 0.04. So that's going to be negative 100 times 0.04. We move the decimal over 2 spots and we get 4 meters per second squared. And it'll be negative. It's plus or minus. And the thing is with it, you could put either plus or minus there because it doesn't tell you if you're looking at the positive amplitude or the negative amplitude. So it's 4. You just have to know which direction it's going, which that's all the negative tells you. A negative tells you if it's going in the negative direction or a positive direction. That's really it. Or, you know, so this is accelerating in the negative direction, which would cause anything that's moving positive to slow down. Yeah. What's your question, Z? Also, now we're going to get into, oh, this is easy stuff. It's the next part that sucks. Because next we have to move in stuff. So how do I know what signifies amplitude? All right. So if we're looking here and we look and it says the block was pulled aside to a distance of 4. That's how I know what the amplitude is. It's got to be 0.04. And that's pretty much how easy it is to connect those things. So we moved the block over 0.04 meters. That was it. You can't have a higher amplitude because you can't add energy into the system once you've let it go, right? So if I have a spring, which I don't have anything to signify, but if I had a spring and I pull it and I let it bounce without adding in any energy, it can only go as far as I stretched it. It can't go any further than I stretched it because that breaks the law of conservation of energy. It can't go if it went any less, that would mean that there has to be another force. We said that there's no friction. There's no other force, so it has to go exactly to where I pulled it. Otherwise, it breaks the world. It breaks physics. And we like to pretend that physics only breaks in space and not on Earth. So, yes, as well as it's the maximum distance traveled from our equilibrium point. Yeah. So, next we're asked to compute the velocity and the acceleration when we're halfway back towards equilibrium from our initial position, which means that we're going to be at a distance of half of our amplitude. So if I do this right here, right, x is going to equal a divided by 2, which is 0.04 divided by 2, which equals, you guessed it, 0.02. So that's how far we're going to be away, and that's our distance at this current time for this. I don't know. Black holes break physics, and I don't want you to ever tell me differently. Black holes completely break physics because it creates an. I'll talk about this after I'm done with AP class. I'm gonna get too distracted. So that's what we have to compute from, and so we have a couple of new equations. Well, they're old to my students, but they might be new to you. And so the thing is, we can't just divide it by 2, and that's the thing. The acceleration, we possibly could just divide by 2. That one might work, but it won't work with our velocity. Velocity is such a weird thing because acceleration is a constant change. And so that constant change is going to be creating a weird change for our velocity. So the velocity won't just be half. Now, if we did our acceleration, right? So our acceleration, in this case, we have our negative k over m times A. We do have our negative 200 divided by 2 times 0.02. That ends up giving us 2 meters per second squared. So that one is half. That one works out. But that's because it's a nice, beautiful algebraic equation that has no weird, funky things. Then we get to the fact of our equation to find the velocity at any point in time in simple harmonic motion of a spring is negative V max times the square root of 1 minus x squared over a squared. So this is a completely different equation, and it basically says your velocity will be a percentage based on the ratio of your distance away and your amplitude. And it's really weird, and I'm really sorry, and I don't have a better way to explain it other than completely re-deriving it. And so we go in, and so we know that our max velocity was negative 0.4, right? Yeah, 0.4. And so that times the square root of 1 minus our new, which is 0.02 squared, over 0.04 squared. And we got to plug all that in. And so I know it looks like a mess and everything like that, and I'm sorry for that. It's really hard to write small with this on this screen. And so when we plug all that in, what we end up getting is negative 0.346 meters per second, which is not half of what it used to be. So the halving does work for our acceleration. It doesn't work for the velocity because of the square root and the addition and subtraction stuff that's going on there. But it was a good idea and a good thought to bring up, because that is something that people would think that, oh, well, it's just half as far, so it might be going half fast. That's not quite entirely true. And so that's kind of how it changes as it goes on. So but that's what we got for it. Now we get to the part that you're all going to hate. And I'm sorry about that, because now we have to talk about the sinusoidal. Yes, the word is sinusoidal. And it's just to talk about how this thing has a trigonomic function attached to it. So how it basically acts as a sine or a cosine graph, and moves in a easy way, as it moves in some might say a simple harmonic motion. And so, you know, because it goes back and forth. Anyway, that's what I'm teaching, is simple harmonic motion. That's why that pun doesn't work. Anyway, so we actually have to use a mixture of an equation that goes on, because it's really weird. And it's okay. This is going to give us, by the way, this is going to give us in terms of RPMs, so revolutions per minute. And that's fine. And that's going to be what it is for our, so that's what it's putting it in there. So now we get to move stuff around and do all that. So our velocity, as we know, we learned this equation that is V max times the sine of 2 pi frequency times time. That's what the equation is. And I know it's such a weird thing. Now, we want to look at this when we're through 5/6 of our oscillation. So 5/6 of a period, which means that our time is equal to 5/6 of the period that we found, which is great. We like that because that gives us something that we can use. So we can go and we already found our period. So we have our 5/6, and that's going to be multiplied by 0.628. And when we put that in, what we end up getting is 0.523. Now that 0.523, that is going to be what we use for our E. And our frequency, we found our frequency earlier. We're going to use that. And so when we plug everything in, we have our velocity, and that equals negative 0.4 times the sine of 2 pi times our frequency, which is 1.592. And we take that and we multiply it by 0.523. And that's how we do all this. And all this, by the way, when you're doing this and you plug this into your TI-84, this is in radians. not in degrees. You're probably used to using degrees for every single thing in physics, and I love you for that because you understand. But understand also that this is going to be in radians because we have a pi there. Pi means radians. Pi is root and it gives us radians. That's how it works. That's just how it goes. So pi is going to give us radians, and that's what we're going to do with it. So that means that once we plug it all in, we make sure we're in radian mode. We'll end up getting a velocity equal to plus 0.35 meters per second. So 0.35 meters per second is what we get for the velocity for that. And now we're done looking at that, which was terrible, and I'm so sorry because we just had to look at the sinusoidal nature. God, I love that word. Sinusoidal. Fun word to say. All right. Last thing, and then I get to be done for the day and go get lunch. So, I haven't eaten lunch yet today. I love you guys. So, now what we have to do is graph the position, velocity, and acceleration of the mass for the first 2 complete oscillations, which will be amazing. So, really, really easy. So, let's look at the position. So, the position, we start off at the maximum amplitude, right? So, we start off at the maximum amplitude. As we get to about half of a rotation, half of a period. So period is the amount of one full rotation, right? It's the time it takes to complete one full cycle. So like if you have a wave, it's the time it takes to complete one full wave. And so what we have is we're at our amplitude here, and we'll be at our negative amplitude at half of the period. And so that way, when we come back up and we go back over, when we get to one full period, we've completed one full wave. And then we just repeat that wave. So it comes back down. Oh, I need to erase that part. Please don't erase the whole thing. Thank God. So this is going to be our 3/4 T. And then 2. Bada bing, bada boom. It looks really bad, but it's a good old cosine wave. It's a good old cosine wave. So now we go and we move on to our velocity, and we're going to use a different spicy color. We're going to use pink. I like pink. So when we start off, our velocity starts at 0 because we're at our farthest point away, and most things, they start at 0 when they start moving. Well, then it starts moving back in a negative direction. And so when it gets to T/2, we're actually at our negative amplitude, right? That's what we just said. So halfway to our negative amplitude is our equilibrium. That means we're at our maximum speed. Then we get back to our amplitude, we're at 0 again. Then we go up halfway, we're at our maximum speed, then we're back at our amplitude again, giving us this nice, beautiful cosine wave, which anybody that knows calculus understands that this is just a derivative of the cosine wave, is negative sine. That's a derivative. That's how it works. And so then what we do is we go and we've got our 3t/4. Of course, I got to do the 3t/4. That's how we're going to get another little bump where we reach this is our equilibrium points. That's when we have our maximum velocity, and it pops back up and does that again. Of course, if it was a nice, better graph, it would look all symmetric and everything. So now last we have our acceleration graph. Now our acceleration graph, it starts pulling back. And so the reason we have to start at our negative max for it, which I got to change colors, don't I? There we go. That purple looks nice. So we're at our negative max. And the reason that is because the acceleration, all that force pulling this mass back towards its 0 position. And so as it's pulling it back, it starts at its maximum, and we get to our T/2. Yeah. Our T/2. Oh, that's a really bad way. We're gonna do that over. And so what we get is this nice, it goes, and when it hits equilibrium, it hits 0. But then the wave starts, the spring starts to push it back. And so it tries to push it back towards the equilibrium. So it gets pushed back towards the equilibrium, and then it goes too far. And so we have that negative pulling it back again, right? That wave look, just trust me on the waves. I know it looks weird and they're not great. And so then as we go, again, we get to our equilibrium point, and it's got a 0 acceleration because we don't have any acceleration at our 0 point. And it gets to its max when we get to the top. Comes back down, gets to its negative max as we go. And so we're left with a negative cosine wave as it goes through for the acceleration, which again follows the calculus that would be going on with this and everything else. And sadly, guys, I went 16 minutes into the bell. Which would have been, for my regular class, this would have taken us a decent bit of time. But I also wouldn't have had to over-explain some of the things. But that being said, if you guys like learning AP calculus and all that stuff, I hope you guys enjoy it. I hope to see you guys on Wednesday. We're going to go through astronomy and AP physics again. We'll be learning simple harmonic motion of a pendulum on Wednesday, and then we're going to practice it on Friday. So that being said, I hope you guys have a great day. Stay awesome and do great things. Please like, comment, and subscribe if you're on YouTube, and I will see you guys next time. Adios.